Asymptotes and in behavior.
So asymptotes, we've kind of addressed a little bit.
They are like invisible lines that a graph approaches but never touches or crosses, or rarely approaches.
Rarely crosses.
Rarely crosses.
Yeah, but always approaches.
Yes. Vertical asymptotes never get crossed.
Never.
Horizontal asymptotes are only really asymptotes out at your end behavior. So what's
Right.
happening really far to the left, what's happening really far to the right.
And really far means bigger than the numbers on your graph or screen. Like really, really.
A lot of times, though, you'll see
a tendency.
it start to get
right,
there.
Right.
So if I wanted to find horizontal or vertical asymptotes, then I could graph this.
Right.
And I could look at that. I do know where my vertical asymptotes are by setting the bottom equal to 0. Could you put this in and graph this?
Yes.
Okay,
we're
thanks.
doing it right now.
Yeah, we're doing it right now. So if I set the bottom equal to 0 and solve, that tells me that there is a vertical asymptote at x equals 1.
Is that x minus 1?
I meant like a colon there, so I don't have too many equal signs. Now there is a way of figuring out what your horizontal asymptote is, but we'll go into that more in the next chapter or something, right?
About how to find the asymptotes?
About how to find the horizontal asymptotes.
Yes, I believe
and
so.
so it looks to me like that's at y equals 1.
I think so.
And so you can kind of trace on your graph. If you trace and go really far to the left or to the right, then you'll see you're getting really, really
You can
close
look at your
to
table of
y.
points,
or
too.
the table of points will work
Because it
as
happens
well.
fairly quick.
Right.
Yep.
Describing the end behavior of the graph. We're going to
Oh,
use...
by the way, on this, for the record, I don't mean to
Yes.
interrupt,
No,
but
fine.
nowhere did Mrs. Stevenson take the numerator and set it equal to 0.
Because all that tells us is the x-intercept.
Is the x-intercept. It does not tell us a domain issue at all. So you'll be tempted, but
You might be.
Just don't.
Might be tempted.
Don't do it.
Now, we are going to start doing in behavior in a very specific way. Back in the day, you may have done like falls to the left, rises to the right, blah, blah, blah.
None of that business.
We're going to do a fancy way. We're going to use limit notation. And we're going to say the limit as x approaches negative infinity. You abbreviate limit with LIN.
Right.
As x goes to negative infinity, what is happening to our function?
Right. What
f of
y
x.
value is the function starting to annoy?
Right. So as I go closer and closer to negative infinity, what am I getting closer and closer to? This asymptote value, which was 1.
So now you may be asking, this whole limit business, I don't get it. Well, limits are a little tricky to get. Super duper important
For
in
calculus.
calculus.
So we're kind of introducing you to this idea with this notation.
Right.
The limit, as x goes to positive infinity, then we'd follow our graph this
Right.
way. We'd say, what are we getting closer and closer to on our function? And again, we're getting closer and closer
Right.
to 1.
Think about a limit like you'd play the annoying game with your brother or sister in the backseat of the car. Oh, quit touching me.
I'm not touching you.
Oh, quit
I'm not
touching me.
you.
That's it.
I'm
That's how
getting
it goes.
really close.
Yeah, not touching.
But I'm not touching.
Ugh.
So that's what a limit does, is it's if we could get closer and closer and closer, what would we end up at?
Right.
And if we could keep going forever, in theory, we'd get super close to 1.
But never touch it.
But technically we never touch it.
Right. Okay, good.